Hi, I'm Mayuk, and today I'll present our work Harnessing Frozen Unimodal Encoders for Flexible Multimodal Alignment. And this is a joint work with collaborators from ML Labs Dublin, UC Berkeley, and TII Abu Dhabi. In this work, we explore how to align frozen unimodal vision and language encoders using lightweight projectors. Our approach builds on the idea that these models already capture similar semantics. So we just need simple projection transformations to bring them together. This leads to efficient, flexible, multimodal models at a fraction of CLIP's data and compute costs. Recently, several works have shown that well-trained vision and language encoders, despite being trained independently, exhibit high semantic similarity. This is based on the idea that these models are trying to model the same physical reality. This leads us to the practical question: can we align them using just simple projections? Through toy examples and real experiments, we show that semantic similarity between encoders makes this possible. With minimal compute and data, we create clip-like models adaptable to tasks like zero-shot classification, retrieval, and even multilingual and localization setups. The Platonic Representation Hypothesis suggests that vision and language models converge towards a shared latent reality. Prior work, including ours at CVPR 2024, shows strong semantic similarity between their embedding spaces. So in this work, we ask, can the similarity be harnessed using just a small MLP layer? Our goal in this work is to leverage the Platonic representation hypothesis for practical gains in terms of compute and data efficiency. To test our hypothesis, we start with toy examples using synthetic embeddings. We generate two embedding spaces with controlled semantic alignment by sampling random base vectors, adding structured noise, and applying random nonlinear transforms. This setup lets us manipulate CKA scores directly, simulating varying degrees of semantic similarity. Then we train a small projector and measure the ease of alignment as the clip loss after 500 steps. The result? As CKA increases, the alignment becomes significantly easier, supporting our claim that similarity in structure makes projection-based alignment feasible. We then repeat the experiment using real embeddings from 9 vision and 5 language encoders. We use a small COCO subset for this and again measure semantic similarity using CKA. The trend holds. Higher CKA consistently correlates with easier alignment using a small projector. This reinforces our core idea: semantic similarity between frozen encoders is a strong signal for learnable alignment. Building on these insights, we propose a simple framework for efficient multimodal alignment. First, we pick semantically similar vision and language encoders. Then we curate a concept-rich dataset with high-quality image and caption pairs. Finally, we train lightweight projectors using a standard contrastive loss. That's it. No fine-tuning of the encoders, just aligning their latent spaces. So why CKA? Interestingly, strong unimodal text performance does not always translate to good alignment. We measure the quality of alignment using image text retrieval scores on Flickr after aligning different text encoders to DynaV2. We evaluate text encoders on semantic search and sentence similarity tasks, but it's not clear which of these actually matter for multimodal alignment. Instead, we find that CKA with the vision encoder is a much better predictor of downstream performance. This highlights that semantic compatibility across modality matters more than unimodal task performance. Since we train only around 11 million parameters, we can afford to use a smaller but higher quality dataset. We curate 21 million image caption pairs with two key goals: high semantic alignment and broad concept coverage. We start with CC3M and CC12M for the alignment and then augment with data curated using 3000 curated concepts. For each concept, we retrieve 2000 image pairs from the uncurated data pool, giving us a rich and diverse training set. We train simple projection heads on top of frozen vision and language encoders. To capture both global and local information, we use separate projectors from the CLS token and local tokens in each branch. This dual branch setup helps preserve fine-grained details while supporting global semantic tasks. Our aligned models achieve clip-level performance, but with far less data and compute. They also generalize well to a wide range of zero-shot tasks, including classification, retrieval, segmentation, and multilingual scenarios. Importantly, this is done without any specialized training data. So no multilingual data, no localization or long context supervision. In zero-shot in zero-shot classification and retrieval, our model uses using Dino V2 for vision and Allroboto Large V1 for text outperforms clip models from OpenAI and Lion. This demonstrates that simple projection alignment, when combined with strong unimodal encoders, can surpass large-scale joint training. We only train 11.5 million parameters while keeping the encoders completely frozen. This allows us to use a high-quality 21 million pair dataset, which is 20 times smaller than what's used for from scratch training of clip. Overall, our approach is 65 times more compute efficient, and this low cost enables greater flexibility in real-world applications by simply swapping out the encoders. Thanks to our modular setup, we can swap in a multilingual text encoder like multilingual MPNet. Even though our model was trained only on English captions, it outperforms multilingual models like MClip, NLLB Clip, and even Clip models trained on Lion 5B, which includes captions in over 100 languages. This shows that the inherent multilingual capability of the text encoder is retained after alignment without needing any multilingual supervision. We also test our model on zero-shot segmentation using just text prompts. The localization ability of Dino V2 is preserved after alignment, enabling accurate segmentation from text even in non-English languages. On English Pascal VOC, we outperform methods like Spark, which are trained with fine-grained alignment losses. And unlike Clip, our model handles multilingual prompts effectively thanks to the strong language encoder. Our model also supports long context queries, thanks to the long context capacity of Allroboto Large. Unlike Clip, which is limited to 77 tokens, our model continues to improve retrieval performance up to 200 tokens. This shows that long context capability of the text encoder is preserved in the joint space, even though we trained only on short captions. In summary, we show that semantically similar vision and language encoders can be aligned using just simple projection layers. This is the first practical use of the Platonic Representation Hypothesis, unlocking clip-level performance with a fraction of the data and compute. Our modular framework enables plug-and-play flexibility, so just swap in any frozen encoder for your task. This approach makes multimodal learning accessible even on limited hardware. We imagine a future where aligning any modality, audio, 3D, or text, is as simple as training a projector. Think of this as sentence transformers, but for multimodal alignment. Just freeze the encoders and align. All our code, data curation scripts, and the concept-rich dataset are available on GitHub. Thank you.